For Friday's lesson, we just have a little bit that we need to finish up here about solving equations using the rational root theorem and using the conjugate root theorem. So not a ton left. And like I had said, it'll definitely be a shorter lesson than yesterday's was. So problem 4, finding all the zeros of the polynomial function. And as you look at what are the zeros of f of x equals x to the fourth plus x to the third minus 7x squared minus 9x minus 18, you realize there should be 4. And it is in standard form. So that's nice. And then we list our possibles. And we use that 18 from the back for the numerator. Our integer factors are 1, 2, 3, 6, 9, and 18. Ooh, lots of them. All right, and then in the front, this is the good news, a 1. So that'll be a plus or minus 1 down here. So we'll have as possibles plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. And as I was talking about in class yesterday, this is really helpful even if we're going to use the graphing calculator, because 18 and negative 18 are possible zeros this time. So we might have to increase our window a little bit when we use our graphing calculator if one of those ends up being a 0. So now what I'm going to do is get my graphing calculator punched in, but I'm going to pause this so you don't have to watch that. Got it all punched into the calculator up there, and then I'd hit graph, and I only see 2, and I remember, wait a second, it was possible that 18 and negative 18 might be up there, so maybe I had better change my x's, negative 20 to 20, so I can see them all. Oh, well, it is just those 2. Kind of looks like negative 3 and 3, so second graph, well, sure enough, there it is, negative 3, 0, and 3, 0. But I'm not getting worried. You know, I know that there's supposed to be 4, and I only found 2. It's just that sometimes it takes a little bit more work to find the others. So negative 3 and 3 from the graphing calculator. And since there are 4 of them, once we are done with these 2, we'll have this down to a quadratic. And that means we'll be able to find those last zeros that we need. So I will do negative 3 first. 4, 3, 2, 1, 0. It's in standard form. Nothing's missing. And we'll do our synthetic. Outside the box, multiply by a, which is negative 3. Then inside the box, add. Outside the box, multiply by negative 3. Go inside the box and add. Outside the box, multiply by negative 3, go inside the box and add. Outside the box, multiply by negative 3, inside the box and add. And that's good news. That means I've verified that negative 3 definitely is a 0 or a solution or a root. All of those things are synonymous. They mean the same thing. Starting with the leading coefficient, outside the box multiply by 3, inside the box add. Outside the box multiply by 3, inside the box add. Outside the box multiply by 3, inside the box add. And this is great news. Negative 3 and 3 are verified. Remainder constant x squared. So what we have left down there is x squared plus x plus 2. And we need to know those 2 remaining zeros. So I think, well, maybe I can factor this. Greatest common monomial factor. Nope, nothing I can take out of all 3 of those. Perfect square trinomial. No, 2 is not a perfect square. Well, maybe some good old-fashioned factoring. Are there 2 numbers that multiply to 2 and add to 1? 2 nice integers. And the answer is no. So this is a quadratic formula problem. But the numbers are nice and small. A is 1, B is 1, and C is 2. And then you just sing the little song in your head. X equals negative B plus or minus the square root of B squared minus 4AC all over 2A. But in the back of my mind, I'm thinking, these are definitely going to be imaginary because we couldn't see them. You know, the real zeros we can always see. So x equals negative 1 plus or minus the square root of 1 squared, which is 1, minus 4 times 1 times 2, all over 2 times 1, which is 2. Negative 1 plus or minus. Well, 4 times 1 times 2 is 8, and 1 minus 8 is negative 7. And of course we can't leave that negative in there, so that'll be negative 1 plus or minus the square root of 7i all over 2. And that's the last two of the zeros that we needed to find, because it's negative 1 plus the square root of 7i over 2 and negative 1 minus the square root of 7i over 2. So that was an interesting one that we did not run across yesterday. Yesterday we had a couple of imaginaries, but we were able to just solve. You know, we didn't have to do anything like the quadratic formula to get those. But do keep in mind, the quadratic formula is only for quadratics. You have to have a 2 as the highest power of your degree in order to be using the quadratic formula. For A, what are all the zeros of the function g of x equals 2x to the fourth minus 3x cubed minus x minus 6? And I see it's a degree 4 polynomial. But while I was at it, I also saw it was missing that x squared term. And I don't want to forget that, so I'd write that down right now. List my possibles, go to the 6 in the back. All the nice integers that divide into 6, there are not a lot of them, which is fantastic. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then on the bottom, we need all the nice integer factors of 2. So let's see what those would be. I will take a 1 through the first time for my denominator, so it'll be 1 divided by 1, which is 1, then 1 divided by 2, which is 1/2. Now I'm done with the 1. I'll use the 2 on the top. 2 over 1 is 2. 2 over 2 is 1, and that's already on my list, so I don't have to write that one down again. 3 over 1 is 3, and 3 over 2 is not on my list yet. Go to the 6. 6 over 1 is 6. And again, we do the plus or minus for all of those. And then 6 divided by 2 is 3, which is already on my list. So with this one, my list of possibles goes out 6 and negative 6 in the x direction. So I should be able to see these with a nice little zoom 6. So again, I'm going to pause this so I can punch that in. You can see, got it all punched in there, and I will try zoom 6. And it looks like we're only going to get 2 real zeros again. There are only 2 spots where we're crossing the x-axis. They do look like nice ones, though. It might be negative 1 and 2. So second graph, and it is. Negative 1 has a 0, and 2 has a 0. So negative 1 and 2 will be the numbers that we do our synthetic with. I'm just going to put GC here because that's what we use to get those. And I'll start with negative 1 synthetically. And I'm remembering that I need a 0 for the x squared term. So it was 2x to the fourth, negative 3x to the third, 0x squared, negative 1x, and minus 6. And realizing, yes, I need to get a 0 when I do the synthetic with negative 1. So bring down that leading coefficient of 2, outside the box, multiply by negative 1, and put it inside the box. Inside the box, add. Outside the box, multiply by negative 1, and put it inside the box. And then inside the box, add. Outside the box, multiply by negative 1, put it inside the box, and add. Outside the box, multiply by negative 1, and inside the box, add. And that is fantastic news. We have the 0 that we needed to see. And now I need to keep going with this since it worked. Trying to get the bars to show up here. There we go. And a 2. Blue is giving me trouble again. There we go. A 2. So bring down that leading coefficient of 2, outside the box, multiply by 2, put it inside the box, and add. Outside the box, multiply by 2, put it inside the box, and add. Outside the box, multiply by 2, put it inside the box, and add. Excellent news. These both work. And we are left with 2x squared minus x plus 3. And we need to know when that's 0. Now, this time I'm not even going to bother trying to factor it and all of that, because I know it's imaginary because I couldn't see it when I graphed it. So we might as well go after the quadratic formula again. So x equals negative of negative 1. Negative 1 squared is 1, minus 4 times 2 times 3, all over 2 times 2, which is 4. Now let's see what's under that radical. 4 times 2 is 8, and 8 times 3 is 24, and 1 minus 24 is negative 23 over 4. And the last thing to do would be to write that square root of negative 23 as either I square roots of 23 or square root of 23I, because we don't have any perfect squares that divide nicely into that 23. So these are our last two zeros here, and they're imaginary, and those imaginaries always come in pairs. 1 plus I square root of 23, and then we've got 1 minus I square roots of 23, both of them divided by 4. So on to the next part of the objective. We are in Algebra 2 talking about sections 5.5 and 5.6 together, and we have different objectives for this one. We're solving equations using the rational root theorem, which is what we covered yesterday, and then we're using that conjugate root theorem, and that's more of what we're going to focus on today. So like it says, complex conjugates, also called conjugates, come in pairs. And we know that about the imaginaries. We've talked about that. A plus bi is there, then a minus bi is there. So the complex conjugate for a plus the square root of b would be a minus the square root of b. And those are irrational roots. Remember, those are things like square root of 2, square root of 3, square root of 5. They're not one of our perfect squares. They don't work out nice. If we put them in the calculator, they end up being some messy decimal without any kind of pattern. And so what we're seeing here is that they always come in pairs. So this works for both the complex, which means our imaginary as well, and irrational roots. If they give you one, you have to know the other one. So you have to figure out what's the opposite here, because they always come in pairs. And that's the conjugate root theorem. So a big part of our objective here. If p of x is a polynomial with rational coefficients, then irrational roots, p of x equals 0, that have the form a plus the square root of b, occur in conjugate pairs. If a plus the square root of b is an irrational root, with a and b being rational numbers, then a minus the square root of b is also a root. If p of x is a polynomial with real coefficients, then the complex roots of p of x equals 0 occur in conjugate pairs. That is, if a plus bi is a complex root with a and b real, then a minus bi is also a root. And that's because in the quadratic formula, x equals negative b plus or minus the square root. So we always get that little plus or minus piece when we're looking for those conjugates. So using the conjugate root theorem, we're going to identify roots. And it says a quartic polynomial has rational roots and has rational coefficients if the square root of 2 and 1 plus I are roots of p of x equals 0. What are the other two roots? So what we have to realize is the square root of 2 doesn't come alone. Negative square root of 2 will also be there. And if 1 plus I is a root, well then 1 minus I is a root as well. So the complex conjugates of those two. And that's all this question was asking for, is what are those other two roots? So down here with number 5, it says a cubic polynomial p of x has real coefficients. If 3 minus 2i and 5 halves are two roots of p of x equals 0, what is one additional root? So this is showing us that we don't have anything additional to do with that 5 halves. 5 halves is a rational number. 2.5 is a decimal, a nice decimal. And so that one, it's done. It comes by itself. It's alone. But 3 minus 2i, that is a complex number. That has a conjugate. So that will be the other 0. And another thing they're trying to point out is that would be all 3 of the zeros since this is a cubic. So cubics, we know, are supposed to have 3 zeros. We are not guaranteed that they are all going to be real. In fact, with this one, we had 1 real 0 at the 5 halves, and then we have 2 imaginaries, because those imaginaries come in pairs along with the irrational roots. So that's what that objective is about, us understanding that we have to have pairs for our irrationals and our complex numbers, which have the imaginary components. So zeros, x equals 5 and x equals -2. We've done this before where we've put it back into factors by thinking of them as x minus a factors. We'd have the quantities x minus 5 and the quantity x plus 2. And we could multiply that together and get the polynomial x squared minus 3x minus 10. So this next problem uses the fact that we can find those factors to write a polynomial. And it's multiple choice, but it says, what is a third degree polynomial? So that means we've got 3 zeros going here. And it's a cubic. Y equals p of x with rational coefficients so that p of x equals 0 has the roots of -4 and 2i. The first thing we have to say is, oh, wait a second, they're trying to pull a fast one, because if 2i is there, -2i is also there. -4 can be alone, because -4 can be written as a fraction. It's -4 over 1, so that's a rational 0. But we need to write it. So this is where we go back and say, all right, got to put all of these in that little x minus a format. So that will be x plus 2i, x minus 2i, and x plus 4, because remember, everything with x looks the opposite. So that's a 0 of -4. And then we need to multiply this out. And we've done this before, so hopefully this is feeling like a lot of review for you here. We know that we should group those 2 imaginaries together, because when we multiply those out, it won't be imaginary anymore. So first times first will give us x squared. We don't bother with outside times outside and inside times inside, because this is a sum and difference pattern. When you have the plus and you have the minus, those 2 outside times outside and inside times inside are opposites of each other, and you get a 0 for the middle term. Minus 4i squared. And then we still have the x plus 4 to multiply by. Now, we have to recognize that I squared is -1. And of course, that's going to change a sign here. So p of x will equal x squared plus 4 times the quantity x plus 4. And then one more time with FOIL, since we've eliminated all those imaginary components in there. First times first, x squared times x is x cubed. Outside times outside, 4 times x squared is 4x squared. Inside times inside, positive 4, positive x gives you positive 4x. Last times last, 4 times 4 is 16. And then we can go back up here and look for our answer. And we see the only one that doesn't have subtraction in it, because our answer doesn't have subtraction in it, is C. And it matches up perfectly. So, wouldn't have had to be multiple choice. Obviously, we had a bunch of work we had to do to get to that point. Now, the got it is what quartic, so that reminds me, I need 4 zeros. What quartic polynomial equation has the roots of -3i, 8, and 2? And right away, I remember, oh, imaginaries, they always come in pairs. But the 8 and the 2, those could be written as fractions, 8 over 1 and 2 over 1, so they don't need a pair. So I'm going to go ahead and call this one f of x, because it said polynomial equation. We could call it y, we could call it f of x, g of x, anything we want to. And x plus 3i and x minus 3i would represent those x minus 8 factors. And then we have x minus 8 and x minus 2. Oops. Waiting for the blue again. There we go. And so I would start by multiplying those 2 imaginaries together. Group those together first. so that we don't have imaginaries as we go through this whole process. First times first would be x squared, and last times last would be minus 9i squared. And then I might go ahead and multiply the x minus 8 and the x minus 2 because I know I'm going to have to eventually anyway. So FOIL on those two. First times first is x squared, outside times outside, minus 2x, inside times inside, minus 8x, for a total of minus 10x. And then last times last, negative 8 times negative 2 would be positive 16. So we will change the I squared to negative 1, and then negative 9 times negative 1 would make that plus 9. And we're not done, but at least we don't have any imaginaries in here anymore that we have to work with. So now we have to take a binomial times a trinomial, and that you do distribution for. So we would multiply x squared times everything in the second set of parentheses and get x to the fourth minus 10x to the third plus 16x squared, and then take 9 times everything in the second set of parentheses, so plus 9x squared minus 90x, and then we need to figure out 16 times 9, which will be 144. And then we'll collect up those like terms, combine them. So x to the fourth is all by itself, so is negative 10x to the third. No more x to the third terms. But we have a 16x squared and a 9x squared, which is 25x squared minus 90x plus 144. So really the only like terms that we had here were the squared terms, but we still had to put those together. So it's definitely a quartic. They said it had to be a quartic, and we've got a quartic. The rest of it is just being very careful with your multiplication and your combining of like terms. Then the last piece to this has to do with the consecutive integers. So I'm going to hold off on that one for day 3. The day 2 assignment is right down here, so page 316, problem number 33, and page 322, number 14, 22 to 25, 30, and 31. Quick reminder that from the 5-5 section, remember that it is a possibility that you might not have any rational roots, but we need to look for them just the same.